So today we'll talk about fossil fuels. What are the fossil fuels?
Coal, natural gas.
And oil, okay? And so we'll see how they're formed. Okay, so let me just start off by showing you that. Look at this. That's pretty neat, huh? What's going on here?
Carbon burning?
Huh?
Carbon burning?
Well, you can't just burn. So there's oil in this rock. This is shale oil. And there's enough oil that you can light this rock. Okay? And actually, U.S. has the largest shale oil deposit in the world. Yeah. All right, so I'm just going to show you a picture and show you how oil is formed, oil and natural gas. Okay. The oceans have a lot of microorganisms, zooplankton and phytoplankton. They're always dying, and they settle to the floor. Most of this is recycled. Only about 1% gets made into stuff that'll become oil and natural gas. Okay, for it to happen, this needs to be in oxygen-poor water. If it's in oxygen-rich water, then it'll get recycled. And then what needs to happen is sediments need to settle on it. Okay, so if you're at the right depth, then clay and sand from inflow of water will settle on top. And then this needs to get buried. So over time, all this happens over millions of years. And then more sediment settles on it, pressure builds on it, and temperature rises. And so if this sediment builds up to about 2 to 3 kilometers, 2 to 3 kilometers is from here to the US 1. That's how much sediment needs to build. Okay, and that happens over millions of years. And the temperature will rise. If the temperature rises to about 80 degrees, this becomes something called kerogen. So that organic matter becomes kerogen. Okay. And if more sediment builds, and so the deeper you go, the temperature rises. And if the temperature is between 90 and 160 degrees Celsius, then that becomes oil. Okay. And oil is less dense than the surrounding medium, and it'll rise. And if there's a impervious rock cap, the oil will collect it. Okay, so you'll have reservoirs of oil there. If the temperature rises above 160 degrees, so 90 to 160 degrees is called the oil window. Okay? So the oil window is 90 degrees to 160 degrees. And greater than 160 degrees Celsius, then you get natural gas forming. Okay, so oil and natural gas are formed from these microorganisms in the ocean. Okay? And it's formed over millions of years. Okay, so the deal really is the following. See, all this carbon got trapped over millions of years, and now we are burning it up in 50 to 60 years and releasing all that carbon in the atmosphere, which is causing climate change. That's the issue. Okay? All right, now let's look at how coal is formed. So for coal to form, again, you need plant matter, but this is bulk plant matter. And so this will happen in swamps and stuff like that. And then if it gets covered, so to turn biological matter into fossil fuels, what you need is pressure and temperature is what you need. And so how do you get pressure and temperature? How do you get pressure? When you bury it under sediments. Okay? And as it gets deeper, it gets warmer. Okay? So pressure and temperature over time, what that does is it concentrates the carbon. Okay? It evaporates all the volatiles, it squeezes out the water. Okay? And so over time, with pressure and heat, the the carbon concentrates. Okay, so the longer you treat it with pressure and heat, the higher the concentration of carbon. The higher the concentration of carbon, the more energy there is per pound in the coal. Okay, so these are grades of coal. This is the least energy content coal, and bituminous, and anthracite. Okay, so lignite is the least energy content on coal. Let me show you the energy content of these coals. All right, I guess we'll come to that one. Yeah, so anthracite, see, this is the energy content, megajoules per kg. Okay. Lignite, that's the least carbon concentration, and it's 16 megajoules. Okay. So this is more than 2.5 times. The anthracite has more than 2.5 times the lignite coal. Okay. And you see the moisture content is decreasing. This is half of this is moisture, and this is only 10% moisture. So you see, that's what that's showing. This is half of this is moisture, this is 10% moisture. The energy content of this guy is 2.5 times the energy content of that. Okay? So the longer you pressure and heat treat biomatter, the better the coal. Okay? The first forests were formed 350 million years ago. Okay, so the best coal deposits are that old. Okay. All right. So you guys get a sense for how these fossil fuels are formed? All right, so now let's look at some of the details. So we'll talk about the properties of fossil fuels and how we obtain them. Oil and natural gas, all you do is find a reservoir and pump it up. Availability of fossil fuels. Why do we use fossil fuels, by the way? Huh?
Well, cheaper, I guess.
They're the cheapest source. Okay. Well, now solar and wind have become cheaper. Okay. Solar, back 30, 40 years ago, NASA used to use them, solar panels, when they sent satellites to space. But back then it was $100 a watt in the 70s. Today it's about 30, 40 cents a watt. So that's how cheap it's gotten. Yeah. So we'll look at worldwide use of fossil fuels. We'll look at the Hubert model. When you find an oil reservoir, how much oil do you think we can pump out of the reservoir?
1,000 gallons?
What's that?
1,000 million gallons?
No. Okay, so let's say there's 100 gallons in the reservoir. With our best recovery techniques, we can only bring up half the oil. It's hard to pump it up. It's hard to, because it's permeating the rock and stuff like that. It's hard to get it up. Okay. All right. So fossil fuels all originate from ancient organic matter that has been subjected to high temperature and pressure. Okay, so you have to subject organic matter to temperature and pressure. And how do you do it? You bury it under sediment. Okay, and you saw that for oil and natural gas, the sediment, how deep do you have to bury from here to US 1? And building up that much sediment takes a lot of time. Inside Earth over millions to hundreds of millions of years. Okay, so you're making this over hundreds of millions of years. So depending on the starting material and the formation condition, the resulting fossil fuels can be coal. So plant matter, you start with plant matter and then you get coal, bulk plant matter. Oil and natural gas are formed from microscopic ocean organisms. Yeah. So oil formed over in the oceans with microscopic organic matter. So how did it end up under land, like in the Middle East and stuff like that?
And water receded over time.
Well, plate tectonics moves all these stuff. As the plates move, it'll end up over millions of years. It can end up wherever. Okay. So the formation of oil takes a significant amount of time. About 70% of all oil deposits existing today were formed about 200 million years ago in the Mesozoic age. Okay? Mesozoic age. 20% were formed about 65 million years ago, okay, during the era of the dinosaurs and stuff like that. And there's about 10% that were formed even older than that, okay, 400 million years ago. So again, there was a large amount of plankton in the ocean back then. Okay. So the formation of oil begins in warm, shallow oceans. When plankton, this is small organic matter, falls to the ocean floor, they consist of animals and plants. The dead organic matter of the ocean floor mixes with inorganic material, and then that enters the ocean by rivers. So this dead matter, when it settles, it has to be in oxygen-poor water. If it's in oxygen-rich water, it gets recycled. Okay, it'll decay. So it has to be in oxygen-poor matter, and then you got to cover it with sediments. Okay, and then how much time do you have to make oil? Then you have millions of years. What do? You just pile it with more sediments, increase pressure and heat, and eventually it'll turn into oil. Okay. So when the temperature of this stuff is about 80 degrees, it turns into kerogen. And then if you increase the temperature and pressure, then it becomes oil. What is the oil window again?
Is it 90 Celsius to 60?
1, yep, very good. 90 to 160. Okay, okay, so mixes with this sediment on the ocean floor forms oil over millions of years. Okay, so again, so here's organic matter falling, and inflow from river and stuff covers it with sediments. Okay, and okay, so to form oil, the following steps have to happen. Dead plankton as well as algae and bacteria sink to the bottom of the ancient ocean, and they mix with inorganic material like clay. So this creates an organic rich mud. Okay. This mud can only form in still water environments. Okay. So if you're churning the ocean floor, you can't form that. The mud cannot be exposed to too much oxygen, okay, or else the organic matter in the mud would decompose by bacteria and decompose quickly. Okay.
Is it hypoxia or hypoxia, right? Or hyper?
No, hypoxia is lack of oxygen.
That's what that.
Yeah. It turns out that only about 99% of the organic matter is recycled. So all the coal and oil that was made from only 1%. Only 1% didn't get recycled. Before this organic matter is destroyed, it is buried by more sediments and lithified. Okay, lithified meaning becomes rock. Okay. creating organic shale. That's what was burning in that picture. This is organic shale. Yeah. If this shale is buried between 2 and 4 kilometers, that's what the distance from here to US 1. Yeah. Its temperature increases due to its location in the Earth's interior. This increased pressure and temperature on the shale transforms it into something called kerogen. Okay? And so that's the starting material for oil and natural gas. Now, if you increase the temperature and pressure on this kerogen, if you increase the temperature to between 90 and 160, it becomes oil. If you increase the temperature above 160, it becomes natural gas.
Oh, natural gas.
Yeah.
So oil is what to what then?
90 to 160, that's called the oil window.
And then past that would be natural gas?
Yeah.
Okay.
And something else called graphite. Graphite is the thing in your pencil, the lead in your pencil. Okay. If the temperature is between 90 and 160, the kerogen is transformed into oil and natural gas. Into oil. Well, okay, so no. Okay, above, okay, so this statement, I gotta correct that. At temperatures higher than this, only natural gas or graphite is formed. Okay, at temperatures above 160, only natural gas or graphite is formed. This temperature range is known as the oil window. Yeah. Rock bodies that contain significant amount of oil are known as reservoir rocks. Yeah. For oil to remain trapped, there must be a thick, impermeable layer of oil to seal the reservoir. Okay, so oil is less dense and it would rise. Okay, so there has to be an impermeable layer, and then you have oil there. Okay, so let me show you a picture of that oil reservoir. Okay, so here's a porous rock, meaning this any oil underneath can rise through. There's water, and there's oil. Oil is less dense than water, and there's natural gas, and there is impermeable rock. That's the seal. Okay. And so if you find this reservoir, you dig a hole through there and then pump up the oil. Okay. And then this porous rock will also have plenty of oil mixed in it. And if you can crush this rock and release the natural gas, that's mostly natural gas and stuff like that, what you can do is you can also pump down steam, hot water, and get this oil flowing up. Okay, when you're doing that for natural gas, that's called fracking, when you're fracturing the rock. Yep. Okay, so impermeable layer of rock to seal the reservoir. If this seal exists, then oil and gas and water are trapped beneath and can be drilled to obtain the oil. Geological changes in the Earth's crust can bring these deposits closer to the surface, or they can bring it under land and stuff like that. So it forms in the ocean, oil and natural gas, and then it's transported over millions of years all over the place. Okay.
Like the whole thing, the whole picture you showed
Mm-hmm.
moves.
Yeah, see, okay, this stuff is only about, let's say, all this thing is less than 10 miles deep. Okay, so now let me show you plate tectonics. Okay. Do you know the radius of the Earth?
Not up to.
Okay. It's 4,000 miles. Yep. The top 40 miles. Okay, that's the crust. That is broken up into plates. Okay. And then this layer, because of the pressure, this is plastic. This is called the asthenosphere. And there's heat rising from the center, so you can think of this as pieces of wood floating on honey. This heat rising will make these plates move all the time. This is 40 miles thick. How deep was your oil deposit?
10.
Within 5 miles. So as this plate moves, it's carrying everything with it. Okay. This plate might go underneath that plate, and then it goes in and melts and all that. This plate moves over, and so you can move them all over. Yeah. Over what time span does all this happen? These plates move at about 2 inches a year. That's how fast your fingernails grow. Yeah, yeah. So let me show you. So there. Okay. So there is that asthenosphere, the orange one. That's the honey. The top layer, that's broken up into plates. And see here, these are the plates that it's broken up into. See, this plate is moving in that direction. That plate is moving in that direction, the African plate. Okay? And the arrows tell you the speed of the plate. The total area of the plates, surface area, is constant. So when you run into each other, okay, one plate goes underneath the other plate. Okay? And then when they get stuck, they're constantly moving, but they get stuck. When they're released, that's when earthquakes happen. Yeah. Why will one plate go underneath the other plate?
Lighter?
Huh?
It's lighter or denser?
That's right. The denser plate goes over the lighter plate. You know? So plates are constantly being created and destroyed. But if there's oil reservoir in this plate, that'll survive. All right. So so geological changes, again, all this stuff happens over 50, 100 million years, longer than that. Okay, again, so to make oil, how are you making oil? From microscopic organisms in the ocean. These settle in oil in oxygen-poor water, and then you gotta cover them up with sand and clay. And then over time, you build pressure and the temperature rises. Um, uh, and the organic matter eventually becomes kerogen. Okay? And we'll talk about kerogen. So this kerogen has been formed over 500 million years, and it's been collecting. And so we'll see this in a little bit, but if you take all the living matter on the planet right now, what is the largest living things? It's matter is in microscopic organism. But you take all the forest, everything, all the living matter, there's 10,000 times more mass in kerogen right now. And remember, only 1% of organic matter was formed into kerogen. So So that's how much kerogen there is. And if this kerogen is submitted to a higher temperature, part of it becomes oil. So coal is formed when dead plant matter submerged in swampy environment is covered by layers of dirt and rock. Okay. So coal is formed with dead plant matter. Okay. And what is it that you have to do? Same thing. Treat it to pressure and temperature. Okay. It is then subjected to heat and pressure over hundreds of millions of years. Over time, the plant matter transformed from moist, low-carbon peat to coal and energy and carbon-dense black or brownish black sediment. Okay, so you got to squeeze out all the moisture, okay, over millions of years, and increase the carbon content. So coal is categorized into 4 main categories: lignite, subbituminous, bituminous, and anthracite. Okay, again, you saw the this has the least moisture content and the highest carbon content. Most of the coal burned in the U.S. power plant is bituminous. Okay. Coal also contains sulfur. Okay. What happens is when you burn coal,
Carbon,
what's that?
those are carbon.
You burn carbon, but you're also burning this sulfur combines with oxygen, it becomes sulfur dioxide, and then it turns into sulfuric acid, and that's the acid rain. So that turns into acid rain again. So sulfur content is determined by the condition under which coal is formed. Low sulfur coals develop in freshwater environment. High sulfur coals deposit come from brackish, swampish water. Yeah. All the coal comes from mines which are underground or above ground, surface coals. Both types of mines. So to form coal, remember you had to bury the plant matter and treat it to pressure and temperature. But over time, with plate tectonic motion, they can reach the surface. Underground mining remains one of the United States' most hazardous occupation, killing dozens of miners every year. I guess mining coal is a hazardous business. All right, so again, the quality of coal is increasing as the pressure and heat treatment lasts longer and longer. Okay, so this is the best quality coal. We use a lot of this coal right now, because that's what's easily available. Okay? So to form coal, you need pressure and heat and time. Yeah? So kerogen is that matter that organic matter is first turned into. Okay, it's so organisms are dying all the time on the surface of the planet. When they die, they decay, and all parts are recycled and reused quickly by the biosphere. Less than 1% sediments. So less than 1% of all living matter sediments. It gets included in forming rocks. Okay. All the sedimentary rocks are, formed in the ocean floor, where clay and sand deposits get deposited on the ocean floor, and the pressure increases and they get compressed. Okay, so those are the sedimentary rocks. All sedimentary rocks include some organic matter that became trapped in the forming process, creating organic shale. Okay. If this shale is buried between 2 and 4 kilometers, then the temperature and pressures are high enough. The increasing pressure and temperature of the shale transforms it into kerogen. Okay, so to make kerogen, you have to have organic matter trapped in sedimentary rock, and you gotta bury it from here to US one. Okay, so now you have the process for making oil, so you gotta go home and make oil. Okay.
See you in a million years.
Huh?
See you in a million
Yeah, see me in 100 million years, yeah. If kerogen is continually heated, it leads to slow release of the fossil fuels such as oil and natural gas. And also the non-fuel carbon compound called graphite. So if you go about 160 degrees, then you make that graphite, the lead in your pencil. You can't burn that. Kerogen is solid, insoluble organic matter in sedimentary rocks. So there's 10 to the 16 tons of carbon. Okay. Of kerogen that's the estimate on Earth. Okay. Exceeding the total organic content of all living matter by 10,000. So all living matters is about 10 to the 12 kgs. Okay. And 10 to the power 16 is tons. Oh, tons. And 10 to the power 16 tons of carbon is in kerogen. So kerogen is your starting point. I mean, kerogen is your base, and you can convert kerogen into liquid or gaseous hydrocarbons. Hydrocarbons are, so petroleum and all are hydrocarbons. Hydrocarbons are compounds that contain both carbon and hydrogen. Okay. And okay. So you see there is the total amount of kerogen. Okay. And so natural gas is a very tiny percentage of that. Okay, so that would be the tiny percentage of gas compared to this kerogen. And and this shows you shale oil is that tiny percent and all that. So a lot of the carbon trapped is in kerogen. Okay. Though it's generally present in very small proportions in the sediments, all kerogen on Earth represents 10 to the power of 16 tons. Only 0.1% of this kerogen turns into coal. Gas and natural gas represent 0.003%. Okay. So the useful fuel is very small portion of the kerogen. Okay, so for your generation, what is the main concern?
Climate change.
Climate change. And why is climate change happening?
Good people.
Huh?
Good humans.
You're burning the carbon dioxide.
Increase of carbon dioxide in the atmosphere. Okay. I'm sorry?
I said cutting down a lot of trees too.
Yeah, it doesn't matter. Increase of carbon dioxide is what you want to avoid. Okay, so if you burn oil and coal, then you are increasing carbon dioxide. Now you could do the following. Instead of burning coal and oil, you could burn wood. Well, doesn't that increase carbon dioxide? Yeah, it does. But if your economy is running on wood, and then you have to replant trees, that'll capture the carbon dioxide. So if the world lived on wood, then it would be carbon neutral. Okay, that's assuming if you cut down 10 trees, you're planting that many trees. So why don't we do that? Why did we move away from that? I mean, that's what was happening 1,000 years ago.
It's expensive.
here is why it's happening. See, the energy density. So that's what this is megajoules per kg. Wood has that much energy, and coal has 3 times the energy. So when you use an energy source, so if you carry a pound of coal, you're getting 3 times the energy. Okay, so that's why the energy density increase. Crude oil has 4 times the energy density. Okay. So it's so we use fossil fuels because they have high energy densities, 3 to 5 times that of wood, and are inexpensive. Okay. You just pump it up for oil or dig it up for coal. And if you happen to be lucky and find coal near the surface, then that's even that much easier. Look at this. So here's a coal mine that's near the surface. Okay. That's very easy picking. So wood can be carbon neutral if one replants trees. Okay, so you could, if you choose to run the world on just wood, that would be carbon neutral. Okay. Unlike wood, fossil fuel use releases carbon dioxide into the atmosphere that was trapped millions of years ago. Okay. So that's the problem. Carbon dioxide causes climate change, and that's the problem. So typical oil and gas deposits are 250 million years old. The efficiency rate of making oil from carbon in plant material is about, so you're making oil from microscopic organisms, the efficiency is 10,000 to 1. Okay, what that means is 20 tons of organic matter produces 1 liter of oil. Okay, to produce this much oil, you need a semi-truck full of organic matter. And millions of years. So oil was first used as fuel in the mid-1800s. So early production wells were in Pennsylvania and Ontario. Okay. So here's a 1859 picture of one of the first oil wells. So oil is a primary energy source. Okay. And the energy available per year from the world oil production is 30 billion barrels. So the world produces about 30 billion barrels of oil a year. And that's 170 quads. Yeah. Do you guys remember how many quads of energy is needed to run the world per year? 600 quads. Okay. And a quad is 10 to the power of 18 joules. This is a quad. And 1,770 of those are coming from oil. Yes, so roughly a little less than a third of the energy that the world uses is coming from oil. Okay, so the world uses about 600 quads, and that's 30% of the world energy comes from oil. So here is a map of the oil reserves so this is that hasn't changed much. So this is 301 billion barrels. Okay, Canada has a lot of tar sands and stuff like that. Okay, and so that's oil mixed in sand, and they have a lot of oil like that. Venezuela, in the Middle East. Okay. So this, we compare the US and Saudi Arabia oil production. Okay. So this is the Hubert model. What this model says is the following. Okay, so you have a resource, and when you first discover it, then you figure out ways to extract it. And as the extraction process gets cheaper and more efficient, the use of that source rises. Okay? And then the use will peak as the source depletes, then you can't use that anymore. Okay, and so once the reservoir is gone, then the use of that source goes away. So it's sort of like a bell curve, and Mr. Hubert predicted this curve. Okay, and it's held true. Okay, so we produce about 2.5 billion barrels of oil per year. Okay, from about 500,000 oil wells. Okay. Saudi Arabia produces 4 billion barrels per year, and this is 15% from about 1,000 oil wells. Okay, so their oil wells are in a small region, and they're gushing oil. So you see, in the U.S., this much oil is coming out from a well per minute. Okay. Production rates per typical well in the U.S. and Saudi Arabia. So this much oil is coming out per minute from a U.S. oil well, and 1,200 liters are coming out per minute from a Saudi well. 1,200 liters is this much. So that's because our oil wells, we are past their peak use, so the oil wells are depleted. What you pump up is crude oil. That's thick stuff. You can't pump that in your car. So you gotta separate the different ingredients, and you pass it through a fractioning column. Okay, so let me. Okay, so here's a fractioning column. You might have seen refineries like this. Okay. So a fractioning column has progressively lower temperatures as one goes up the column. So here is, you heat the crude oil, and you see the temperature is decreasing as you go up the column. What that does is, okay, so it turns out that the smaller the molecule, the lower its boiling point. The heavier the molecule, higher its boiling point. Higher, lower, okay, so what this does is, okay, so you pass this crude oil, heat it, the temperature is low here, so anything whose boiling point is below 350 degrees, that'll remain liquid, and you pour it out. Stuff whose boiling point is over 350, under 350, will rise up as gas. And then this will rise up as gas, and then lubricating oil, the stuff you use in cars, this boiling point is 300 degrees. So if the temperature is about 300, so this will stay liquid. It's between 300 and 350, it'll be liquid, and it'll pour out. Okay, so diesel is residue fuel oil. lubricating oil. Diesel has a boiling point of under 260 degrees, and it becomes liquid here. It's under 260 and above 300. I mean, under 260 and below and above 180. Okay, so it'll become liquid in this window and pour out. Kerosene. Okay, so that's how you separate all the different stuff. Okay. Petrol is gasoline, okay, and then refinery gas. Okay. So a fractional column has progressively lower temperature as one goes up the column. Crude oil is heated to a furnace at about 400 degrees Celsius so that most of the hydrocarbons are vaporized. The very heavy hydrocarbon or impurities fall to the, so this thing has boiling point over 400 degrees, okay, and that's asphalt, tar, and all that kind of stuff. The very heavy hydrocarbons, okay, 42 gallons of crude per barrel make about 19.5 gallons of gasoline. Okay, so 42 gallons of crude, you get 19 gallons of gasoline. So half of the crude is gasoline. That's what that tells you. Okay. 9 gallons of fuel oil, 9 gallons of fuel oil that is used for heating up north and all that. 4 gallons of jet fuel, 11 gallons of other products. That adds up to more than 42 gallons because something called refinery gain, the processing and chemical changes increases the volume. Okay, so that's it. All right, so here are the components of crude oil, and there's the boiling temperatures, and so you can figure out where in the column you'll find them. Okay, and here are the uses of them. Okay, so of course gasoline is an automobile fuel. Fuel oil is used in home heating. Okay, has anybody lived up north? Okay, where have you lived?
I'm from West Virginia.
Okay, did you guys use fuel oil, heating oil?
Yeah, and like coal and stuff is big up there.
Mm-hmm. Coal for heating homes? Oh, yeah. So in general, heavier hydrocarbons have higher boiling point. Okay. So they can be separated by allowing vapors to travel up a fractional column with progressively lower temperatures. Okay, now we'll do just a little organic chemistry. Okay, we'll talk about alkanes. Are you taking organic chemistry? Do you not like organic chemistry? You not?
It's just when you said it, it scared me a little bit.
No, we'll just do simple stuff. Alkanes are long chain hydrocarbons. Okay. So carbon as if you look at carbon, its atomic number is 6. What does that mean?
6 electrons?
Hmm? It has 6 electrons. So here is the nucleus. The innermost has 2 electrons. And the outermost shell has 4 electrons. Hydrogen atomic number is 1. It has 1 electron. Okay. Carbons, this is called the valence shell. A valence shell, 8 electrons in the valence shell is full. Okay. So carbon's goal in life is to get 8 electrons. So that's what it does okay, in everything it tries to do in life, it's trying to get 8 electrons. All right.
What time is your class until?
40, 50, something like that.
I would talk to Sandy. She double booked us in a room, but she said that there's supposed to be no classes in here. So, I mean, I'll go down and talk to her real quick too,
Mhm.
but, yeah.
All right, so okay, its goal in life is to get 8 electrons. Look at this guy. He's willing to give up his electron. He'll share his electrons. So here's carbon, here's hydrogen, CH4. Carbon bonds with 4 hydrogen atoms, each one sharing an electron. What is this guy?
Nothing?
Methane. This is natural gas. That's the main content of natural gas. Okay. So alkanes are so each carbon has to form 4 bonds to get that extra electron. So you see every carbon is bound to this guy, this guy, this guy, this guy. Each guy sharing a pair of electrons. This carbon, okay. That's how the carbon atom is getting 8 electrons in its valence shell. This is an alkane. Okay. And the more carbon atoms there are, the heavier the molecule. Octane has 8 carbon atoms. Okay, and if you add up the hydrogen, it's 18 hydrogen atoms. Okay, that's the main content of gasoline.
Is there something that reached at the end of it?
I'm sorry?
What about the last scene, the last carbon? Did you touch anything else?
Oh, well, I didn't draw it. I just got lazy.
Oh, it just keeps going. Oh, okay.
You can keep doing that. Okay.
Oh, you keep going,
Right.
basically. Oh.
Okay, so if you just wanted to make a 4 carbon thing, so you can make this as long as you want. Okay, so those are alkanes. Okay, so here, methane is a 1 carbon, ethane is 2 carbons, propane is 3 carbons, butane, pentane, hexane. Okay, and these are the boiling temperatures. So you see, octane's boiling temperature is 125 degrees Celsius. Okay, so not too much higher than. Okay. These are the molecular masses, the energy per kg. Okay, so this is a gas. This is megajoules per kg, and this is energy per molecule. Okay. And electron volts is a unit of energy. So this is heat of combustion. Okay, that's how much heat you'd release when you burn that molecule. So we saw the location of oil deposits. Okay, so oil deposits are under impermeable rocks. Okay, you have to have a porous rocky bottom to let the oil up. Okay, and so oil is less dense than water, and that's a deposit. So deposits are trapped under oceans or can end up under land because of continental drift. Okay, so how fast does continental drift happen?
2 inches a year?
2 inches a year. Oil and gas are usually trapped within porous rocks that act as reservoirs. The reservoirs has a cap of impenetrable rock, preventing the oil and gas from rising. Usually water is below the oil and natural gas. When a well is drilled, initially the underground pressure forces oil and gas up. So when you first dig, the pressure will just make it come up, the oil come up, okay? So you don't even have to pump it. About 10% of the oil can be recovered this way. Then to sustain removal, pumping is commonly employed. Additional recovery is achieved by injecting water into the reservoir to provide increased pressure. Okay. And then after you gotten about 10%, then you increase the pressure to bring this oil up. Even with secondary recovery, less than a third of the oil is taken out. Okay, so even with pressure, only about a third of the oil comes up. You're able to bring up only a third of them. Tertiary methods include injecting steam into the ground. The steam heats the oil, making it less viscous, allowing it to flow more easily out of the rocks. Some polymers are also used to force the oil out of the reservoir rocks. The use of enhanced recovery methods increases production from 10 to 30%. So even with all the enhanced techniques, over 50% of the oil is still unextractable. Only about half the oil is extractable. Okay. To optimize the use of petroleum resources, it's necessary to convert some of the less needed refinery products to more needed forms. Okay? So what we are saying here is some of these less needed refinery products need to convert it into more needed forms. Okay, these guys are just bigger molecules. So by heat treatment, you can crack those molecules. Okay, so you can crack them. Okay, longer chain molecules can crack them. So to optimize the use of our petroleum resources, it's necessary to convert some of these into more needed forms. In most cases, this involves breaking down heavy hydrocarbons like tar and paraffin to make lighter hydrocarbons in a process called cracking. This involves heating the hydrocarbon to a high temperature. Now, heating costs you money, but if you're gaining more out of what if you're gaining more than what you're spending, then you'll do it. Okay. Gasoline typically contains 500 different hydrocarbons that have between 5 and 12 carbon atoms per molecule. Okay. So gasoline is between 5 and 12 carbon atoms. Its average density is about 720 kg per meter cube. The density of water is 1,000 kg per meter cube, and this is a meter cube, like I said. A substantial fraction of these hydrocarbon components of gasoline have molecular mass similar to that of octane, and 8 carbon alkane. Okay. All right, we'll stop here today, and then I will finish this lecture next Tuesday.